I will do this later.
Sorry?
You want to know some more?
No, because I'll knock it over. It's quite a lot of expensive equipment here. Okay.
I kind of want to. And then.
Expensive and typewritten rather than make it. I think so. But no time on that. I think we do. Yes. Seems to be different. I know. It's good. Sorry, Cal. Yes, we want to address it.
Okay, test. Okay, super briefly before we start, I am told that informally, Philippa is organizing a fighting games night and that there is news for that. So if you're interested in doing that, then go find her and check the Zulip. Okay, that's that. So we're now going to listen to Bob tell us more about type theory and implicit complexity.
Thanks, Sean. Okay, let's do a recap from last time. So the recap is that we saw two linear type systems for that I claim capture polynomial time. I gave you a completeness proof for one of them, and I think I will put in the Zulip the completeness proof for the other one. But that only shows that we can express all of polynomial time, but doesn't yet show that we can only express polynomial time. So the goal of this lecture is to try to convince you that you could be convinced that there is a proof that you'll get polynomial time. So there's a lot of detail, and I haven't got time to go through all of the detail. There are some Agda proofs on GitHub that you can check out if you want to. And the way that we're going to prove this is by using a realizability model. And last time I introduced the high-level ideas of realizability models, which are as follows: that we want to interpret some kind of typed lambda calculus. And the way that we do this is that we assume that we have some kind of underlying model of computation that I'm just going to abstract here as there's some set E of expressions or evaluatable things or programs. There's some set V of values, and there is a predicate eval, which says that if I have this program on this input, then I can get this output. And I'm kind of implicitly assuming here also that it's deterministic. So if you fix these two, there's only at most one output you're going to get. Then what we're going to do is interpret types as pairs of a set. This is A with vertical bars, meaning it's the carrier of the type, with a relation between values and elements of the carrier. So this relation tells us that for some particular element of the carrier, this value is its implementation. And so there's two important things to think about here. One is that some elements might not have an implementation. And another one is that a particular value may have many implementations. So it might have 0 meaning true in Unix, everything else means false, right? So it could have lots of implementations of a certain value. But this is part of the specification of a type. When we give a type, we not only say what its values are for the carrier, we also say how it's realized by low-level values. Then to interpret a term, which I'm just abstracting here as from one type to another, and if we want to do contexts, we're going to build them up as like tensor products of types. So interpret a term as, well, it's a function between the two carriers, such that there exists an E, which is a program or an evaluatable thing, such that for all A in the carrier of the input and all values, such that that value realizes A, then there exists a final value such that the evaluation gets us that final value, and the final value realizes the output of the function. This is kind of like, if you sort of stare at it hard enough, it's a little bit like a Hoare triple, right? We're saying this is the precondition. If you give us something which is about the implementation of the input, then we get an implementation of the output at the end after evaluation. This is the precondition is you give us a good value, post-condition, we get a good value out at the end, which matches the specification of the function itself. So this is our kind of what do we mean? And this is it is implementable. And what we're going to do is see how to twist this a bit so that this statement here will actually say, and the program runs in polynomial time in the size of the input. Okay. Any questions on this? Yes.
What is F framed over?
Oh, F, this F.
Yes, and then the other F as well, the underlying F.
All right, so this F is just the name of this morphism. And one of these things consists of a set theoretic function from the set, this set to this set, such that there exists an E.
Okay.
Right, or you could think or type theoretically it's a pair of this and this, except this is meant to be mere existence. The meaning that to consider two of these morphisms equal, you only compare this part, not this part. So two morphisms are equal even if they have different realizers. Okay. As long as they have the same set theoretic function. Yeah.
So do we need vertical bars around the F on the bottom right?
Oh, yes, okay. Yeah. Any other?
Yeah, so
Margaret?
This so this abstract computational model, that the underlying computational model, like so this like how do I get an intuition of an element of like something like a value, like it's something that's not like what is actually this V?
Oh, right, the coding V, the big one.
Yeah.
Yeah, so it depends on what you want to do.
Okay.
So from what I don't have time to describe a whole thing, but imagine that this is lambda terms.
All right.
These are particular lambda terms that you think are values in the call by value sense. And then this eval is if I take this lambda term and apply it to this value, then it beta reduces to this one. And that could be the meaning of this.
I mean, that's one way to look at it. Like,
yeah,
I could think of maybe a Turing machines and then some notion of values.
Yeah. So this could be Turing machines. This could be binary representations of numbers. This is if this is the initial tape, then this is a final tape.
All right.
Yeah. So this is a super general notion of computation. Yep.
So there are elements of A that are not realized. And so can functions that act on elements that aren't realized just do whatever they want on those elements?
Yeah.
Okay, cool.
Yeah, so this is important to well, what doesn't this say? If you don't fulfill this, then the evaluation could do anything it likes. So we're only saying if you give it good inputs, you'll get good outputs. But if there are no good inputs, the program can do whatever it wants. It does also say that this will terminate, right? So in the course of doing this, we'll also prove that every program terminates in the sense that there is a V, or there exists a V prime such that it gets to it. Which you could say is implicit in the fact that this is a total function, but that doesn't actually prove that the evaluation is total, like without doing something else.
So going back to eval, is it built in that it's necessarily called by value or?
No, no, no. No, no, so E and V could be the same thing. Yeah. Okay. Right. So what we're going to have to do is some things. So we will have to combine the two examples I gave last time. One was tracking the sizes of data structures by using natural numbers as the realizers. So we need some way of accounting for, well, we need A, sizes, and B, potential. And what I mean by this, I'll make this more rigorous, which is if you have a thing and you give it something of size n, how much work is it going to do? So this is going to be a polynomial. And then we need a notion of evaluation that is costed. And then we put them together. To make our, okay. So the real tricky part here is the first one. We need a way of accounting for not only the sizes of things, but their kind of latent potential. So if you imagine everything in this system, so one thing that's sort of implicit here is that these are untyped, right? I'm not distinguishing between different types of E. I just need to know that it evaluates correctly, but there's no a priori typing. This also means that every value, especially when you have higher order functions, you have closures, the values themselves may be heavy in the sense that they contain data which takes up space, but also when you apply it to something, they have some kind of, they do some work. So if this V is a function, when you apply it to something of some weight, it does some work. So we need a kind of notion of resource which both accounts for the sizes of things and how much work they'll do when they do something. So I'm gonna, yeah.
If I interpret like the abstract computation model as LFPL itself, like I mean the same thing itself.
Yeah.
Then can I think of V as the normal form? So I mean, by which for example, when you give semantics, like it could have like different like terms that could reduce to a normal form. So for example, when I take, I mean, I think of it sets like there are different things, and I take some normal form, then it could have like when I give semantics, V cross that inside A. So when I say like inside V, let's say put a normal form of term, then A can contain all the terms which could reduce to that normal form, right?
Yes, we could do that.
Alright.
Yeah, so that would be one particular one. It wouldn't help us prove
Yeah,
the property we
but
want in
just
this
to
case.
understand,
But
like
yes, yeah. Yeah, so that is actually the kind of model that we used in a proof of like normalization by evaluation here, right? So you would say, and there you might be more careful about the types, but you would say that particular value is realized by the terms of that type. And then this in the end would say that it evaluates to normal form. So you'd sort of simultaneously prove that it evaluates to normal form and maintains the data. So this realizability technique is extremely general by slotting in the right E's and V's. Okay. Right, so to account for the resources, we're going to use an idea from Ugo Darlago and Martin Hoffman called resource monoids. So if you think back to the example from yesterday where I used natural numbers to act as the realizers, and this was a monoid under addition. And the idea was that if two things use, if we have something that uses resources n and something that uses resources m, then we add them up and we get the resources of the whole thing. So these resource monoids are going to be an abstraction of that general idea, but also have a general notion of difference. So if you imagine that we start a computation with some amount of resources alpha, and we end it with beta, then there's some difference between them that we can use to pay for any computation that happens in the middle. This is what this thing is going to be, which is a kind of abstract subtraction. So a resource monoid consists of a carrier set M, or a resource monoid M consists of a carrier set M bar, and a difference operation that goes from M bar cross M bar to the natural numbers extended with a negative infinity. So the negative infinity accounts for when so if you think what's going to happen is we assume this one's a bigger one than this one. If it's not, then we can't get a difference between them, and we say it's negative infinity. And if we order these natural numbers with negative infinity at the very bottom, and then 0, 1, 2, 3, 4, 5, 6, then we'll get sort of things to work out nicely. Well, abstractly, what this is going to be is like this minus this is this. But if this is smaller than this, then we're going to say it's negative infinity. Okay, and these have some axioms. So we're going to say that I'm going to use alpha for the elements of these algorithms.
Could you write slightly bigger? Because the superscript is very hard for me to read.
Oh, right, the subscript.
Yeah, sorry. Thank you.
Okay, so if we're subtracting something from itself, then it's at least 0. It's going to be 0 in most cases. Oh yeah, so, and the carrier set which has a 0 contains a 0 and there's a plus. So that's a monoid. And then this slightly odd looking law, that if we take the difference from alpha to beta and the difference from beta to gamma, and an inverse triangle. I hope I haven't got the less than nowhere to right, so if we go from alpha to beta and beta to gamma, that might be better than going straight from alpha to, so it's like an inverse triangle. And if you stare at these for long enough, you can sort of come up with a sort of simplified way of seeing why they work, which is that in terms of enriched category theory. So the category theory Chris was showing you, there's always a set of morphisms between every two objects. Here, we're taking a natural number or negative infinity between every two objects. So somehow we're measuring the distance between these as the difference between these two is not as a set of things, but just as a natural number. And then this says that there are identities, and this says that there are composition. So we can compose alpha to beta and beta to gamma. We get alpha to gamma. And then finally, this is going to be a symmetric monoidal enriched category, which says that the difference between alpha and beta is always less than alpha plus gamma and beta plus gamma. Right. So this says that roughly speaking. So if we've got the difference between alpha and beta, we can add a gamma to both sides. Or another way of looking at it is a bit like the frame rule, right? If we could get from this pre-state to this post-state, then we can add on some extra stuff which gets carried along for the ride. Yeah.
So this is what are the sum? So I guess the question is, what's the sum is?
Oh, the
we
sum,
don't really
right? So this
have-
is something I'm assuming exists.
Oh, okay, okay. And it's like a monoid on this, or just,
Yes. Yeah.
so there's like an identity.
Sorry.
There's an identity on,
Which is 0.
yeah, okay.
It's commutative, symmetric. So yeah. So yeah, you can treat it as strictly symmetric monoidal. Yep.
I feel like that the second axioms with the first one implies that dm of alpha alpha is always 0, or am I wrong?
Yes. Yes. I think you're right. Yeah.
Okay.
Yeah. Right. So yes, I'm assuming this is already a monoid plus this thing. I would say as a kind of practical note, if you try and formalize this process in a theorem prover, like Agda anyway, trying to assume this is a monoid and then sort of stating that all these things are, the D is invariant under the equivalence of the carrier gets horrible. A nicer thing to do is to specify all of the monoid things just as elements of this which are equal to 0. So, for instance, associativity. So, for instance, all of these laws, you just write them in as free kind of transformations of potentials. And this makes it quite nice and easy to what we're going to do later on, which is construct chains of these things to try and prove that going from this potential to this potential kind of yields a certain amount of resource that we can use to count the steps in their program. Yep.
If you're using equations where d of something equals 0 to represent the monoidal identities, should the top equation there be d of alpha alpha equals 0 rather than greater than or equal to?
You can prove that it's the same.
You can prove that it's the same. Got it.
And finally, we're going to need a
I had a question. The potential in this case, is this related to also like the physicist's method in amortized complexity
Yes.
analysis? Okay.
One of the bankers or physicists.
Yeah, the banker is the one with the credits. The physicist is the one with the potential.
I guess this is more like the bankers because we're going to allow these to sort of be accumulated throughout the data structure.
Ah, okay.
Okay.
Thanks.
Okay, and finally, we're going to have a way of injecting just natural numbers amount of resource into here, so constant time computation, such that the difference between the accounted thing and 0 is going to be okay. So this is what we're going to use as our kind of costing for measuring the amount of costs associated with every value in our system. And the simplest version of a resource monoid is where the carrier set is the natural numbers, and this difference really is negation, where it's negative infinity if the negation doesn't work in natural numbers. And then all of these laws hold, and the accounting is just the identity. I've got a horrible tingly feeling that one of these equations is back to front. So but there is an Agda file which you can read, which has them all correctly in.
Which ends are capital?
Oh, they're all capital apart from this one, which should be an N. And I've changed.
Oh, yeah, account is an additional structure of the file?
Yeah, account is additional structure. So we also say that there should be some function from the naturals into the carrier that satisfies this, which is going to allow us to pay for constant time.
But it is part of the structural resource monoid, or?
Yes.
Okay. Yeah. Sorry.
And because I'm going to need it, a sub-resource monoid is a resource monoid where the carrier is a subset of the other carrier, and the operations are all the same. It's closed under these operations, in particular the counting. Plus. Okay, so the reason for this is that we're going to use a sub-resource monoid to account for whole programs, and resource monoids themselves to account for values within the program. They're going to be slightly different things. I'll come on to why. But if you think about it, a whole program does not contain any data which can be iterated upon. It just has potential to do something, whereas the values themselves have data which can be iterated upon. They can be accounted for differently. Okay, so the basic example. Difference. So let's assume we have a resource monoid that we want to use, and a sub-resource monoid that we're going to use for top-level terms. So that's the amorphisms in the category we're going to build. Now, we also need some kind of notion of computation, like the E's and V's we had before, that's costed. So as I said, there's many ways of doing this. You can make an operational semantics that's indexed by the number of steps somehow. So I'm just going to assume, again, that there's an E and a V with now an eval. That is this ternary relation. Properly. That instead of going to prop, now goes to the natural numbers plus infinity, meaning that we can get, if we apply the expression to the value, we result in this value in this many steps, or we don't ever do it. It's infinity, right? So it's just impossible to get to that final value. Okay. So, and also to make sure this actually makes sense, you've got to make sure it's plausible in polynomial time, right? So this will actually be computable by polynomial time. Like by a Turing machine, it's going to use some proportion of the number of steps it says it does, which is a polynomial, right? Because otherwise you're doing something very, if you say it takes so it takes 5 steps, but actually it takes some huge number of steps in the sizes of E and V, then that's not going to be a plausible notion of computation. So we do have to be careful that given some notion of what the sizes of E and V are, the number of steps is complexity-wise plausible. Now, types are interpreted as again, a carrier set. But now this is a three-way relation between values, elements of the resource monoid, and elements of the carrier of that type. Right, so now we're saying this element of the carrier is realized by this value, which is the implementation in our cost model, in our computational model. And also it contains the resources in this sort of identified by this member of the resource model. And then terms are interpreted. So again, we have A with its realizability relation, B with its realizability relation, and F. So again, we have a function F such that there exists a program such that for all V, alpha, and A, such that V and alpha realize A, then there exists a V prime and a beta, such that, and before we said that the evaluation just happened, this was true, but now we evaluate V to V prime in fewer steps than, oh, sorry, there also exists a gamma in M naught. So we have some potential associated with the program itself, and it comes from a sub-resource monoid, because this sub-resource monoid will be things which don't have any weight to them, just the ability to do something when they have things applied to them. But yeah, the costing must be accounted for by starting with the alpha, which comes from the input. So that's the resources associated with the input, plus the resources associated with the function itself. And then we get the resources beta at the end. And that the difference between the start and the end must be greater than the number of steps needed to do this. I notice if we can't do it, if we've got infinity, then we're not going to get anything big enough to fit this in. If this is negative infinity, then we're not going to be able to evaluate it. And the program is actually correct. So we get this at the end. So this V prime and beta, so the final potential and the value that comes out the end is a correct realizer for the semantic meaning of the function. Okay. This is how we add this idea that we attach potential to values, and then we pay the difference in potential between the sort of pre and post pays for the cost of the execution. So one thing I think would be interesting is, are there other abstract notions of computation which aren't necessarily valued in the naturals, right? So before we had prop, which either it did or it didn't happen. Here we have the naturals, like how many steps it takes. But could this be a probability? And somehow we attach, I don't know how to do this, but somehow there is a kind of, we pay for uncertainty to happen during the program. Or it doesn't necessarily have to be the natural numbers, it kind of some more structured costs, like what are we paying for as we go? And that's paid for by the difference between the start and the end. So I think just by possibly thinking outside the box a bit and abstracting, we could get quite a few different sort of notions of paying for things as we go. Okay.
I'm a bit confused why there's no condition on this gamma or the y. I don't know what it is, like this.
Oh, the gamma?
From M0.
So this gamma is the potential which is associated with the function. So we're going to see later on that this is actually going to be the polynomial, which tells us how long the function takes to run. And it appears here. So this is saying that, so if you want this function to, if you've got some function, and we want this to actually work, typically what this is going to do is to pay for anything which is done by the term, which isn't paid for directly by the input. So I'll do an example.
Nice.
Okay.
Can you take the previous slide? Yeah, so that model symbol in the final, I mean, yeah. So what does that exactly mean? It's not the models as in the previous.
This one.
Okay, so there should be a type annotation. Oh, okay.
Yeah, so these depend on the type. Like to say what it means to be a realizer of this thing depends on the type. Okay. So first, I'll do 2 example types and then an example term to show you how these things fit together. So let's say we've got 2 types A and B. We can make their tensor product as well. It's going to be the carrier is going to be the Cartesian product of the carriers. So semantically, the tensor product, its values are just pairs. And now, when is it the case that a value and a resource realize a pair of semantic values? Well, just as last time, we're going to do a sort of day-style convolution. We're going to try and split the resource and the value into 2 bits, and then they're going to satisfy the A and the B specifications, and then they have to add that back up to the resources we started with. So we're going to say there exists a value 1, the value 2, beta 1, the beta 2, such that V is equal to value 1 and value 2. So here I'm assuming our values are closed under some kind of pairing operation, right? So we've got to have some notion of pairing in our implementation language for this to work. Also, that the difference between beta 1, beta and beta 1 plus beta 2 is greater than or equal to 0. So somehow we can split beta into beta 1 and beta 2 to get the 2 halves out. And typically this will just be 0 because we won't want to throw anything away. And then V1 and beta 1 support A, and V2 and beta 2 support B. Okay, so the kind of typical thing for doing these kind of resource conscious product constructions is that we have in the same way that Vikram was talking about this morning, this is kind of Kripke style semantics, but here we're splitting the worlds or members of the post set into 2 halves and then using them separately to satisfy the 2 halves. Yeah.
I think beta isn't bound anywhere, right?
Oh, that should be alpha. Sorry. Yeah, thank you. Yeah, so alpha splits into beta 1 and beta 2, V splits into V1 and V2, and they separately support the 2 halves of the product. Okay, and let's try and do lollipop. So now, again, the underlying set is going to be all functions from A to B. And the realizability says that some value, and I write gamma here, realizes some function f if, and then this is just really recapitulating the definition of the terms, but at the function with a few sort of fiddling bits, because this is a value representing a function, so we have to sort of apply it to its value, to its arguments, and so on. But we're just going to say for all v alpha or v prime, alpha and a, if v prime and alpha support a, big A, then there exists a v double prime, and the beta. So eval application of the right. So the only wrinkle here is, well, two wrinkles. One is that this v is a value representing a function. So this is the program which takes its input and then runs this whatever representation of functions we're using on the function represented by this value. We're just assuming that whenever we do that, we get out this thing at the end. Yeah.
You've been a bit implicit about what's in M0 and what's in M here. So
That's
gamma is in
the second thing I was going to say is, yes, this is in M, unlike the one that was in M0, because these are closures, so they contain data. So we're going to have closures which close over data values, but whole programs don't close over data values. So in particular, we don't have any constructors in our language, so we cannot construct iterable things in whole programs. So you can't write a program that has a constant which is going to have a resource associated with it. So that's going to be the difference between the M0 and the M, is that the M0 won't have enough resource to build a natural number by itself, only to write programs which, when applied to things that have resources in, will consume time. But these ones, yes, this gamma is in M because it's a closure now, and it may have iterable values in its closure.
Hello.
Yeah.
Just to clarify, the f of A is just f applied to A, right?
Yes.
Okay,
Actually,
thank you.
so the distinction between the M0 and the M is that the M0 contains things which do not have any iterable data in, but do have functions in which, when applied to iterable data, will do some work. This is quite a very important distinction for this whole thing to work, because otherwise you can write programs which themselves contain the ability to make new data.
Can you just quickly say again, what is the app of
Oh,
V?
so app. Okay, so I'm trying to not be too prescriptive about what programs and values actually are, but this is, but I'm making a distinction between programs and values. So this, if this value is something which somehow represents a closure, then app is the program which, with that closure and an input, sort of applies that closure to this input. So this is app is apply. But it takes its argument from here rather than. Okay. Right. So let's try and do a term. So let's say we want to do the rule in the linearly typed lambda calculus, which realizes this. Okay, so this is one of the typing rules of the linear lambda calculus. we saw on Tuesday. And what we want to do is, given a realizable interpretation of M and a realizable interpretation of N, get a realizable interpretation of the pairing that's going to do the right thing. Okay, so that means we've got a function. Yeah, confusingly called M bar. It's going to go from gamma to A, and there's going to be some EM which realizes this function, right? And some gamma M, which is the resource that goes with it. This is the program. This is the resource. And similarly, we have this, well, we have the same thing for N. And so what we need to do now is, well, it's sort of obvious what the function is going to be that does this thing. It's just going to take the gamma comma delta. We can just think of it as the gamma tensor delta.
Delta.
Yeah. Oh, yeah. Delta. All right. Right. So the input's going to be a pair of a gamma-y thing and a delta-y thing, and we're going to put them together. Yep. Find you again.
Should the arrow for N be a lollipop?
No. So these are set theoretic functions. These are the semantic meanings of the terms.
Then should the M arrow be a arrow?
It is. All right. Right, so we need to, so the function is going to be the meaning of M. Gonna take a G and a D. Like that. Okay, so that's the kind of the set theoretic meaning of this function. And now what we need to do is two things. We need to build a program which implements this in our model of computation, along with enough resource to pay for it when we actually run it. So this is where being fuzzy about what the programs are is going to come back to bite me, but let's assume we have some kind of a normal form where we do lists of things. So let's say the realizer for N is going to be let x1, x2 equal x. I'm assuming the input's called x. Let y1 equal, and then we apply the realizer for EM to x1. Apply the realizer for EN to x2. And then finally we pair them together, right? This is a implementation of the whole thing written out in this very kind of so rigid style. In fact, these might be expanded out onto paper. And now we have to come up with a costing as well. So we have a cost. And the way this is going to work is, let's assume that each one of these lets takes 1, plus 1 to build the pair at the end, plus whatever we need to build this. And for the purposes of formalization, commutativity is a nightmare. So what I'm going to do is write this out as we account for the one step at the start. So this is ACCT1 plus, and then we pay for the M, and then we pay for its let, and then we pay for the N, and we pay for its let, and then we pay for the pairing. And then the thing we have to now check is what was on the other slide about when we evaluate this, not only does it do the right thing, which we should get from the fact that these actually realize the right values, but also this is enough to pay for it, plus anything that comes from the input. And now we'll know that from the input, it's splittable into two halves. So what we'll end up with is this added to a beta 1 and a beta 2. The beta 1 and the beta 2 will have to come over to next to these. That'll pay for whatever they're doing. And then we'll make sure at the end, we'll get whatever residual comes off these two as the final potential. Okay, so that's kind of rushed, but really the way to sort of construct the interpretation everywhere is just to write little programs that sort of compositionally stick together to make the whole thing and account for the costs. Yeah.
So, like, can you explain that M1 inside bars? Like, it's, I understand it's a function that like
this one.
No, like, yeah. So, yeah, that yeah. So, what does that mean? Like M inside bar, like it's a function.
All right. So this is just the name M inside bars. It's meant to be the semantic interpretation of the M term.
Okay, so this lambda, like that's in the meta level?
Yes,
Okay,
this this is just my notation for writing a set theoretic function. Yeah, yeah.
So, and the equation for gamma you put there with all the count ones.
Yeah.
You said resource monoids were commutative, right? So,
Yes,
so
yeah.
is there a difference between that and just account 4 plus?
No, there isn't, except when you're trying to do it in a theorem prover.
Okay.
Yeah. Really, yeah. If you imagine the execution's going to
Nothing
run
more
top
needs
to
to be
bottom.
said then there, yeah.
Yeah. The execution's going to run top to bottom. So the only thing you have to do is the fact that due to the way that the evaluation's defined, the resources for the input are actually added on at the start. So you need to sort of swap them over to the right points. And then it helps that you can account for things as you step through the execution. But yes, it would just be add 4. Yeah. So 4 is the cost of pairing plus the cost of the subterms is essentially what's going on. Okay.
You put in lambda GD. Does that work, or do we actually have to do something nightmarish where we disentangle those resources?
So this GD is the set theoretic interpretation of the gamma comma delta.
Yes, that's
Yes.
why I'm asking.
All right, right.
if we have to do
Yes.
something
Okay.
nightmarish.
So this is where I'm just playing fast and loose with yes. What I said on Tuesday was they could actually be a permutation of these things. The right way to do that, well, the right way to do that is to not use this formulation and to use quantities. The other way of doing it is that you have exchange as a separate rule, and that just does the right thing for free. Yeah. Yeah. Right. Okay. So what we've got so far accounts for resources as we go. But so far we can still only write linear time programs because, well, at least with the resource monoid we have so far. So I'm going to end today with resource monoids which are suitable for polynomial time. So I'm going to define 2 different ones because we've got 2 different polynomial time systems. So remember we had the one where you had natural numbers you could iterate over, but not construct, but you could duplicate. And the kind of guiding principle there was that things you iterate over should only come from the input. And you can duplicate these to allow nesting of iteration, but you're not allowed to construct your own things to iterate over. The second one was this LFPL system with the diamonds, where we were allowed to construct new things to iterate over, but only if we made them by grinding up our input into diamonds. So we were allowed to sort of take our input apart into diamonds and turn it into new things to iterate over. So one, we've got a fixed input, which is sort of global across the whole program, and we can share references to that input to allow iteration over it. The other one, we can reform the input and take it apart and share it around in the program. And this will show up in 2 different resource monoids. But these both have the same carrier. So the elements of these will be pairs of a number and a polynomial. So n is a natural number. This natural number is going to represent the size of the data structure. So that's actually the size of the natural number, the input. And p is a polynomial with natural number coefficients. So this is sort of enough to be able to express, maybe over approximate the time taken to do things. So if you think of this as kind of the n is the kind of dead weight of a piece of data. It's the kind of the weight it takes up, the size of it. The p is the kind of potential it has. So when we give it something of size n, it's going to do p of n operations, or might do almost p of n operations. So the n is the data kind of resource. The p is the dynamic resource. And then the way the two resource monoids differ is of how these are added together. So we're going to have the max poly is that n and p plus m and q is we take the maximum and we add the polynomials. Right, so this is going to be the one where all we care about is that there is one input size. We may have forgotten some of it along the way, so some of the numbers might be lower, but overall we're just taking the maximum of this, which is going to be the input size. But we still add these potentials. So if this accounts for running one program after another, we're going to do polynomial time thing plus polynomial time thing, so we need to add these things together. The other one is sum poly. And this is for the cons-free system. And here we add together the sizes. And this makes sense if you think about how the diamonds work. When we construct a successor, we're adding a diamond onto an existing number already. So we add these things together. So you can see here that if you think about how a successor would be realized in this system with the maximum, it's not going to work because the diamond would have one, the natural number we're trying to take the successor of would have something, but the maximum would still be the number of the natural number we're trying to add onto it. So we wouldn't have enough to pay for a bigger natural number. Again, we add this. And then both of them share the same difference operator. I have written down. So this is going to be P of m minus Q of m if oh yeah, sorry. Let me write A and B. Where? No. BAQA. Right, so the difference, so we start out with some data of size A and a potential P. And we want to end up with data of size B and potential, so polynomial Q. So the number of steps we get to use is the difference of the two polynomials with the starting size of data, which we're assuming is bigger. So actually, in most cases, A and B will be the same, unless we've thrown some data away with the affineness of the system. So this is the sort of total amount of steps we can use between the two halves. And this only applies, of course, if the size we start with is bigger than the size we end with, so the same as these length spaces, and if the polynomial is big enough to account for the steps in between. So if Q ever gets bigger than P, then we're stuck. So otherwise, we don't have enough to pay for it, and we return negative P. So the way you can this is a little bit baffling, but if you imagine that we want to end with nothing, so Q is 0 and B is 0, then what we're going to do, the difference between some resources with polynomial P and 0 is always going to be P applied to that number of resources. Right? So if B and Q are always 0, then the amount of steps we're allowed to take is that polynomial in the size of the input. And the other part of a resource monoid is that accounting for A, it doesn't go in the size, it goes in the polynomial. So we have a constant polynomial for the size, right? So this is the part that pays for computation. This is the part that pays for data. And so that means that M0 consists of all of the parts where the data section is 0. Okay. So I claim that with this resource monoid, or one of these two resource monoids, every program which is realizable in the semantics I gave you will run in polynomial time in the size of its input. And then basically this is a little world to live in, and you can construct whatever constructions you want to build things which will interpret the programs in the source language. The nice thing about this is that you can make up another source language which is interpretable using these same constructions. It doesn't have to be the same as my one. So this is a kind of, we've constructed a category of polynomial time computations, and it's up to you to work out how to interpret things into that category. You have to make up some language, you can do that. So this is not just a language for making polynomial time computations, it's a category of polynomial time realizable set theoretic functions. Okay, so next time I'll move on to dependent types and extend it with linear types, so we can do this but with dependent types. Okay, thank you.
More questions? Okay, I have a question. Does this slide here tell a story that could translate directly into something like Granule, some graded model system? Because these max poly and sum poly to me seem like they should correspond to some semi-ring that you could grade by.
Oh, right. Not directly. So these don't appear in the type system. These are just used in the semantic meaning. I think so, but it's not as straightforward. Yeah,
thank you.